Hello, everyone. On this presentation, I will give you a topic, and that is related to the federated learning. And for the title of our manuscript, it's called On the Convergence of Federated Learning Regression on Power Grid Environments. And we are from Suncheon National University. These are the contents, and we will start from the background as well as the state-of-art researches that has been conducted related to the federated learning, and also we'll focus on the regression-based federated learning, and also we will look into some data set level of analysis that is related to the regression-based federated learning, as well as the convergence optimizations in federated learning with a case study that we have implemented some real practice data sets in South Korea. And we'll get to that in later points. And also we will go through some experiments inside the power grids, and we will conclude our paper with some conclusions. For the simple knowledge of the federated learning, so it's an optimal framework in a distributed environment where all clients accommodate to build a stronger global model via transmitting its unique parameters instead of transmitting the local data sets, meaning these types are all local data sets. Each has its own unique features as well as distributions of the labels. And these are the local clients, and each local client has their own deep learning models with certain parameters, with of course different parameters, because it was basically trained with different database local data sets. So it transmits the weights and also bias too, instead of sending the local data sets to the global server, and it aggregates it with simple aggregations. In this case, it's the mean or average, and it builds the models, and it transmits back to the locals. And it was first introduced in the communication efficient learning of deep learning networks from the decentralized data, which was presented by McMahon. And also another distribution environment for the backgrounds. We focus on the power grids, such as smart grids and also the microgrids. And the overall objective of the power grid is to optimize the DER, or the abbreviation of distributed energy resources, to ensure the efficient energy consumptions to build the eco-friendly environments. And also, the federated learning itself is a very suitable environment for the power grid settings in order to collaboratively optimize the energy consumptions and also the energy productions in a dynamic situations. And we studied this via convergence analysis and empirical simulations. So most past studies in federated learning is mostly focused on the classifications, or the classification objective inside the domains of supervised learning. And the regression-based federated learning is not well studied for its comprehensiveness, while aggregations, and the simple difference or the arduous task that incurs the hardness is the first, classification. It's a predefined class labels, and they are stochastically definable, or which is equal to the soft predictions in every local client, or it's basically a deterministic values, which we can quantitatively evaluate the performance between 0 to 100%. However, in regression, it's comparatively a difficult task, for its ground truth varies through every local client with high variance, and also differentiable based loss functions, as well as performance estimation ranges with a higher unit than classifications. And we define this as a non-deterministic feature. For the non-deterministic attributes, it's a daunting task, while convergence compared to a classification objectives. And we look into some limitations. We classify or we categorize into the two domains, which is the data level and also the algorithmic level. And in terms of data level limitations, it's basically it's the non-IID dataset in real practice. So like most datasets are mostly skewed, biased, and as well as easily influenced to the heterogeneous environments, and this incurs a higher heterogeneity while aggregations. In algorithmic level, it incurs the poor aggregation based on the nonlinear. No, actually, like it trains the local datasets with nonlinear fashions. And inside deep learning, that's what the deep learning mostly do. And when it aggregates inside the global server, it's basically a linear aggregation, which so when we aggregate the local clients in an efficient way, it will generate bias model, or worse, it may cause divergence inside the law space. So we look into some analysis of heterogeneous datasets in regression-based red learning, and we look into a non-ID and IID cases. So we have categorized into the three cases in non-IID datasets. So first of all, the case A, we defined it as a dataset volume may vary. So like there may be numerous local clients, and each client incorporates their own datasets, and meaning it the dataset itself, the volume of the dataset itself may vary to each client. And the case B, the label distribution may vary as well. It's pretty simple, and we define this as a Kullback-Leibler divergence. And in case C, the label distribution in time series sequence may vary too. So this is pretty simple. Like in terms of time series, the x-axis is time, and there are certain amount of data set that is distributed within the time domain, there may be some difference. This is what basically it means. So these cases are the main factors that encourage the non-IID series. And if we look into the non-IID cases in federated learning algorithmic view, or to be specific, data sets inside the federated learning. So we use these two cases in a local client level, and these two cases into a single global communication level, and also this final case, two cases into a total global communication view. In each case with odd numbers refers to a non-IID cases, and the even cases refers to a IID cases. So if it would be great if the listeners or the audience could refer to our manuscript. And we move on to the convergence optimizations in federated learning. So we implemented a real practice data sets that we have acquired from the open data portal provided by South Korean government, and we have collected the solar power generation amount from these three regional cities that are distributed in South Korea within the periods of 2017 January to 2021 August. And so to a simple visualizations, this figure indicates the solar power generation amount that is distributed within the time. Axis is the time, and y-axis is a generation amount. So this shows a very typical type of solar power generation amount, and this, however, is a sort of non-IID case that is not typical. And also you could see that the distributions is quite different between those two. And we assume that the adequate form, which is this one, and compare the overall difference within the cases A to C. And we have quantified the degree of non-IID of each day-based solar generation amount. And based on those datasets, we have trained the LSTM in a single local client inside the Federated Learning. So these are the hyperparameters and the layer structures of the LSTM. And based on the regressions or the MSE loss, so if we look at these three, the training dataset was D1, which was the Sejong, and D2, and the Ansan, and D3 was the Yeongnam. And you could see that the it has been trained fairly well, but the MSE is pretty high with the with having higher than like 60 or around 60,000. But if you take a look at these three outcomes, you could see that the training performance has been gone down until around below 50. Oh, and they are same units. And also in this case, we have used the federated averaging in three locals. So this is a federated learning based training performance. And so we have done the monthly training with 70 epochs and merged them. So this 70 is local epoch, and 48 will be our global epoch or global communications. And in total, we have 3,360 epochs. And you can see that the training performance is doing well. And this is a training loss, and it's the validation loss. And here, we have so accumulated the local epoch ones. So that's why it shows the 48. Yeah, so you can see that the training loss as well as validation loss goes down, and these two as well when the local epoch equals to 70. And also this is the heat map that we have shown, and you could see that the locational one, which is Sejong, Ansan, and Yeongnam, the yearly based Pearson correlation coefficient shows the very high similarities. However, when the year becomes different, the correlation decreases a lot. And also, we defined a theorem based on the empirical experiences and lemma as well. Please refer to our manuscript for details. And finally, we have focused on the update periods. So the case A refers to the daily update period, and case B is the monthly period. Case C is the yearly period, and we have confirmed that the yearly periods or update periods, yearly update periods shows the better or the highest performance compared to other cases. So for the conclusion, we defined that the variable scenarios of the locally collected non-IID datasets, and such as the quantification scheme of a non-IID degree in a regression-based federated learning network with a local and global perspectives. And also, to the best of our knowledge, this is the first study covering the domain of local non-IID datasets in federated learning regression since diverse studies were previously focused on the federated learning classifications. Thus, this research offers feasible cases that illustrate the ambiguity in the federated learning regression model. And we suggest the theoretical convergence analysis and federated learning regression optimizations, while the local training dataset holds the IID and non-IID attributes. And we propose an effective methodology to enhance the convergence rate. Finally, we conducted the validations of our analysis through multiple experiments inside the federated learning model within the real-world solar energy generation dataset covering the periods of around 4.5 years, which will enhance the usability and performance of the federated learning regression in future applications in the smart grid system. Thank you very much for listening. If you have any questions, feel free to send us an email, and please refer to our manuscripts. Thank you again.